Yes, so we're heading towards the toric code still. We will get there, at least in some fashion today, but before so we need to get a little bit more theory under our belts so we can talk about the toric code in this stabilizer formalism, which we'll talk about shortly. These are the references, so this one's the same as last week, and then also the paper that basically introduces the toric code by Kideev is a good read if you want to read it. So, recall from last week, this is just one of the theorems we had, and it will sort of crop up again, in particular the stuff surrounding this, where we have this condition for error correction being able to occur for a set of elements or error elements for this quantum operation that models our error channel from last week. So I hope everyone remembers a little bit about that. We'll go on to the stabilizer formalism. So we're going to start off with a definition of the general Pauli group. And it's defined to be the group of n-fold tensors of the following elements. So we're going to be considering subgroups of this general Pauli group. So we'll put up a definition about that now. It's on the sheets as well. And you remember last week that a quantum code is a subspace of a Hilbert space. We're going to be able to use this formalism to define these codes, to define the subspace of a Hilbert space, which we'll see as we go along. So we're going to define this space V sub S to be the subspace So basically this subspace Vs is invariant under this subgroup, the action of that subgroup. Okay, so invariant subspace.
I would like to make one comment. I mean, this bracket with all these elements over there, that looks a bit mysterious maybe, but what it actually is, it's just taking x, y, and z, I mean the Pauli matrices, and then taking all products of them. Here's the
yeah. I mean, and the inclusion of these is to keep it so that it's a group, right? That the inclusion of those coefficients. Yeah. Yeah.
If you take x and y, the product of x and y, you get I times z.
Yeah.
You need all of these with up and minus and all that.
And so it's not explicitly formulated in here, but pretty much throughout today, we're going to take implicit in this definition of stabilizer for this subspace that S does not include minus I. And also we want all of the generators of S. So if we write S as a set of generators, then these all commute. And are independent. And so what I mean by independent is that you can't write one of these generators as a product of the other one. So if we took one of those generators away, we do get a strictly smaller subgroup. Yeah. All right, so we have our first proposition. So if we have a stabilizer group, stabilizer group with these conditions, then we see that Vs is 2k dimensional if this group S is generated by n minus k independent and commuting elements. Okay, so we're going to go through proof of that. The proof does require a result that I won't prove at all. It's sketched. A proof sketch is in the notes, and the full proof is in the textbook, which I had up on the board before. All right, so what we need, dilemma, or it's a proposition in the textbook, dilemma that, I'm going to write it down as lemma, so let S be as above. And then fix an I in the range 1 to n minus k. Then there exists an element of the general Pauli group such that G anti-commutes with the GI for the I that we've fixed and commutes with all the others. So we're just going to use this fact in the proof. All right, so let our stabilizer be this, with all those independent and commuting, and such that minus the identity is not in this group, and let X be a vector in here. And so we're going to define some projectors. So for each j, this projector here, just the I plus minus 1 of the xj, gj, is a projector onto the plus 1 eigenspace of gj. So we're going to write down the projector for the code. I'm just going to write it as p, or you can view it as p with zeros up in this vector here, the vector x. That's the projector onto the subspace vs. Okay, is that clear for everyone so far? So in light of this lemma, we're going to write down a specific element of Gn. So for any x prime in z2 to the n minus k, define hx prime to be this product. Such that the hi are these elements that anticommute with the gi and commute with everything else. Okay. The notation with the xi up in the corner here, basically if xi prime is 0, then we just take this to be the identity of the group, the trivial element, and then otherwise it's just hi. All right, so this allows us to define some new projectors by considering x prime, sorry. So you can see, can everyone see how this works with this definition over here? Or should I spell it out a little bit further? Spell it out? Yeah. So let's consider x prime, just the one in the first spot, and zeros everywhere else. So I've just pulled out that first term because this one's going to anti-commute with this G1 here, but all the rest are going to commute with the Gj. So we get 1 minus G1, so it's I. And then the product so everyone's clear with that step. So H1 dagger cancel here. H1 G1 H1 dagger is going to anti-commute because we have H1 G1 H1 is minus G1. And then so this all commutes here. Yep. So I just want to point out at this point, so we just sort of hit the pause button on the proof. Hopefully this kind of looks a little bit familiar from last week. So coming out over here, remember from last week we defined these projectors pk via some unitary acting on the code projector like this. And that's exactly what we've got here. Unitary, code space, code projector, unitary again. And that gives you this new projector pk. Okay. So the proof continues just by noting that all of these are the same dimension as PS to the zeros. Sorry? Yep. Yep. And we also note that for distinct x, that these projectors are orthogonal, which again we saw last week in the pk case as well. And this is because the intersection of +1 and -1 eigenstates for any one of these generators is trivial. So we have all these projectors of the same rank. We also note that their sum equals the identity. The identity acts on an n-dimensional, to the n-dimensional space. So we have, 2 to the n minus k dimensional or rank of projectors. So that implies the rank of p is 2 to the k. That finishes the proof. All right, so now we come to the definition of a stabilizer code.
In case anybody else was a bit confused about this projector, note that G squared is 1 for all these group elements.
Yeah.
There's also
Plus.
I. Plus or minus.
Oh, right, plus or minus 1, right? Yes. Yeah, okay, that's the real check the projector actually squares itself. It's there.
So definition of stabilizer code is exactly what we'd expect, given what we've just sort of been through, defining the subspace Vs. We're just saying that this sort of notation suggests that we're encoding k qubits into k logical qubits into n physical qubits, which is exactly what we've done here. We've shown that the space is 2 to the k. All right, so we come to the theorem. That's the analog of the theorem put up right at the start, which we saw from last week, about error correcting conditions for the stabilizer code.
Sorry,
Yep.
so these GJs, in principle, they're just random elements from Gn. They might square either 1 or minus 1 this times level. So,
Yep.
that's exactly the reason why you exclude the case minus 1 in
Yeah. So there is I think an exercise in the textbook that says if you have like minus I, if you don't have minus I and S, then you can't have like, plus I, you can't have I times the identity in there as well and things. Yeah.
Okay, so then all the GJ squares 1, therefore this is actually a projector.
Yeah. Okay, so this theorem says that so long as we have this set of error operations elements from Gn such that this product here is always either in S or not in the normalizer of S, then we can correct for those errors. Okay. So one thing to note, which is in the proof of this theorem, or is it written in the proof?
Set theory here is confusing me. It's a constraint is to say something not in that set complement. What you said out loud said it could be outside the normalizer.
Yeah, so if we can correct for errors that aren't in the normalizer. So we can correct for errors such that this product for all j and k is not in the normalizer. And we can also correct for them if they are in the stabilizer, because that's trivial, because if that product's in the stabilizer. I mean, this is basically in the proof of this, but I can just write it here. If we have this case, and this is in S, then, I mean, that stabilizes whatever this is, like this is in the code space. And then this is an S that stabilizes it, so we trivially have that equals P. Makes sense? Yep.
Okay, so we want EJ dagger EK not in N of S, or EJ dagger EK in S or J.
Yep. Is that clear for everyone? Yep. All right, so what I just sort of said in words just then is the proof of if this is in S, then we can correct for it, so we do the other if it's not in the normalizer. All right, so let us first note in this proof the normalizer of S and the centralizer of S are the same. So the centralizer is always contained in the normalizer, so we just need to show the other direction, which we do by contradiction. So in particular, we have this case, so if it's not in the centralizer, then we have that E I is not equal to I, like this. So we're assuming it's equal to some other element that's not I, but as we sort of already talked about, we can only have these two cases for these E and Gn. And because we're already assuming that minus I is not in S, then that's a contradiction. So if E is in the normalizer, it's not in the centralizer. Is that not making any sense? Yeah, but that's why isn't that the proof of this saying that they are equal? So by contradiction, it's a very trivial contradiction, but Okay, so let's suppose that for all jk such that j is not equal to k, ej dagger ek is in Gn set minus the normalizer. So this is the other condition. So we already spoke about when this is in here. So we're now talking about when this is not in here. All right, so we're considering the case when this product is not in the normalizer. That means there exists a G in this stabilizer that anti-commutes with this. And we're going to find the projector like we did in that last proof. And we're just going to assume that EJ dagger EK anti-commutes with G1. All right, so what we're trying to show that this condition is satisfied, or this is equal to alpha times p. Well, yeah. So in this case, we have this. So I've written the projector out in the product form, like over there, and then I've pulled the I plus J1 term past this, and we know that it anti-commutes, so it comes out as 1I minus G1. So again, written this projector in the product form, pulled out the I plus G1 term out here, and then we have, so just these close together, the intersection of the +1 and -1 eigenspaces is trivial, so that goes to 0. that pretty much finishes the proof, because that gives you this matrix alpha ij. If this is in the stabilizer, then we have 1 here. If it's not in the normalizer, we have 0. Okay. Alright, so let's quickly write down a definition, just because it parallels some of the definitions from the classical code case, classical linear code case. So they just define the weight of an error as just the number of terms that aren't the identity in the tensor product representation of this error E. And the distance of a code is the minimum weight that it can correct for. Minimum weight error it can correct for. Yep.
Comment on the relationship that comment is to actual error correction. What the H is doing is flagging errors for -1.
Yeah, yeah. And so, I mean, when you do the error correction, you take a measurement of these projectors, and that'll tell you sort of what type of error and where that error is. So we'll see in the toric code case that it tells you the location and the type of error that occurs, and then you can correct for it because you sort of know the location and the type of error. Yeah. Yeah, yeah. So, I mean, we'll see in the toric code case that this set of stabilizers is going to come in like 2 different types. One sort of will detect X errors and one will detect Z errors. Yeah, so that's not overly explicit at the moment, but it hopefully will become so. Yeah. So stabilizer code of distance n. Distance d. This is called an NKD code. All right, so let's quickly see an example before we get onto the toric code. Let's fly through it. So it's the example that we sort of saw last week of the bit flip code, the error channel, the bit flip error channel. So I'm pretty much just going to write it down. So remember, we had VS was span of these guys. And to write down S in this case, we have these stabilizers, recalling that Z operator Yeah.
Distances V are correct less than 3 years.
You can correct to, so code can correct for T errors. Yep. So I don't really want to spend too much time on this because we want to talk about the toric code, but pretty much you can see that each of these operators will stabilize those elements. Hopefully, Z acting on 0 on the first one, Z acting on the second one, Z acting on the second one, Z acting on the third one. And for this case, okay, so you just get 2 minus signs, so it comes out to be the same. All right, I don't want to spend too much time on that because we want to get to the toric code. All right, so I haven't left myself enough time for this, but basically the toric code, we're going to consider a square lattice on the torus. So we saw a couple of weeks ago with Will's talk that, I mean, you can take a triangulation of the torus kind of like this. Essentially what we're doing is we're not really thinking about the diagonal edges at all, we're just thinking about the square edges. And the way that we get the state space for this code is by attaching a qubit to every edge. So if I was to draw dots for qubits, they come in all these guys like this. Okay, I won't do the whole thing. You have diagrams in the notes. So what I will do is just let V denote the set of vertices. And I just want to be clear, the vertices are these guys, not the dots that I've drawn on. And similarly, yep. Let E denote the set of edges. Hopefully it's not too confusing because we're talking about E for errors as well, but hopefully it's clear from the context. And let capital P also not to be confused with projectors, the set of plaquettes, which is just the faces. So this is a plaquette in here. All right, so the toric code is a stabilizer code. Hopefully you could have guessed that because we've been talking about stabilizer codes. And they come in 2 different types of stabilizer. So you're going to write it as AV is the tensor product on edges that are incident to V. And to follow Kitaev's notation, you write it like that. I might also start writing it just as a tensor product of xj, like that. Okay, so I might swap between them.
Maybe you should write the element space as a tensor product.
So you want it like that? Yeah. Okay, yeah, so the state space is just the big Hilbert space of all the qubits, which is all the edges. Okay. So we have these vertex operators, tensor product of X operators around all of the edges incident to a vertex here. I shouldn't write a dot because I've just said I'm not going to. So around a vertex, and similarly we have the plaquette operators, which are Z operations around a plaquette. Okay. Yeah, just boundary of the plaquette. Yeah. All right. So this is our stabilizer group. We just got to note one thing though before we talk about the code subspace, that these projectors are not all independent currently. So we have the following conditions: that if we took the product over all of the vertex operators and the product of all plaquettes of these plaquette operators, we get the identity. So that's not all independent. So for n by n lattice, so we have n squared vertices, n squared plaquettes. We don't have n squared independent vertex operators and don't have n squared independent plaquette operators. We have n squared minus 1 of each. Okay. Yeah, so I care because when we write down the code space, we can write down the dimension independent of the specific lattice. So I guess I can write that over here. It's in the notes, but if we're talking about the dimension of this guy, so I mean we had 2 to the k. K in this case so we have number of physical qubits. This is the size of the edge set, and then it's minus the number of independent stabilizers here and stabilizer generators. And this is why I want to have, we have to consider this consideration, because I mean if we write this out, so we have the Euler characteristic hidden way in there. So basically I wanted to show you this to show that the dimension of this code subspace is independent of whatever lattice we draw on here. Okay, so it doesn't even have to be a square lattice, it can be a more arbitrary one. We still get the same dimension code subspace. All right, I don't know how much time I'm going to have to get through some of the rest of it.
Yeah, I think it's fine to take the time. Take about 15 minutes.
Yeah, okay. Yeah. All right, so we've seen the dimension of the code subspace. Now we sort of want to look at what the elements are of it, the basis elements in particular. So the way that we want to relate this to the homology of the torus, basically I want to also consider the dual graph. So dual graph is going to be drawn in blue. And basically, you're just putting a vertex of the dual graph in the middle of every plaquette of the what we call the primal graph, and then you join up edges where edges join vertices, and the primal graph is joining between. Sorry, we put an edge of the dual graph between every plaquette of the primal graph. Okay, and so we're going to use the dual graph to talk about VS, in particular the homology of the dual graph. So just to sort of go back to what we saw a couple of weeks ago in Will's talk, we're just going to set up the chain complex for the dual graph and for the primal graph. So let C2, C1, and C0. So this is going to be the Z2 free vector space over edges, over plaquettes in the primal graph. C1 is Z2 free vector space over edges in the dual graph, but it's also, very closely related to the vector space of edges in the dual graph. And then C0 is the vector space over the vertices in the primal graph. I'm going to write down everything that has a prime is for the dual graph. So hopefully people remember a little bit about how we constructed homology from these chain complexes a couple of weeks ago, because we will start to take a basis for the big Hilbert space by assigning a 0 or 1 to every edge. So that's the big Hilbert space, and then we're going to start looking at what condition we want to satisfy. So we can write VS as a set of all vectors in the big Hilbert space such that AV psi equals psi, VP psi equals psi. And we're going to do this sort of one by one. We're going to look at vectors that satisfy this, and then the vectors that satisfy that. And to look at this one, we're going to have to talk about this chain complex, which is for the dual graph. Okay? All right, so let's just denote this basis by curly B. So all these elements of the basis are the elements of the vector space over the edges and the dual graph and the primal graph. Okay, having this condition, this. Yeah. So we're assigning 0 and 1 to all these black edges, and we also just assign the same value to the blue edge. So what are you saying? Yep.
Otherwise, it's going to get pretty.
Okay. Yeah. So elements in here correspond to elements in these vector spaces, and in fact, when we apply this condition, it's going to be exactly the elements that are in the kernel of this map here. And you can think of that as just saying that the sum of these labels around any plaquette has got to be 0 mod 2. All right, so then we're going to look at basis vectors of Vs. So, yeah, I should probably write up. We saw a couple of weeks ago that the homology of the torus Z2, Z2. These alpha are going to be vectors that correspond to elements of the 0, 0 labeled homology class of the dual graph. Okay, the beta correspond to elements of the 0, 1 labeled homology class of the dual graph. The gamma are 1, 0 labeled homology class, and the epsilon are the 1, 1 labeled homology class.
Some coefficients A alpha.
Yeah. 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 So when we can start, so this is only, so far we've only considered the BP, this constraint here. So if we start to consider, I'll just write dot dot dot, so that's, you know, saying what I just said. When we enforce the next constraint, this constraint is going to say that all of these coefficients are going to be equal. Okay? Yep.
The kernel of delta 1 prime is precisely the condition that would pick out the co-cycle. So this is the homology of the dual graph is the cohomology of the torus.
Yeah. Yeah, I mean, I didn't sort of want to talk about cohomology because we haven't really seen it in this series of seminars. Yeah. All right, so I think we should probably go to an example because it will be a little bit more instructive. So you have the equivalence classes for each of the homology classes, right? And we're taking a sum over all elements in the homology class. So every single one of these alpha, and every single one of the beta, every single one of the gamma, every single one of the epsilon satisfy this. But if we just looked at each one individually, they're not going to satisfy this condition. So which is why we're going to have to take a superposition. I'll try and explain it better when we actually look at a specific example now. But for a long time, I just thought that we could take, an assignment of zeros everywhere on the lattice, and that would be in the code subspace. But it's not, because it's not invariant under the vertex operators. So I'll just draw another one. So basically, just like what I've just said, if we had zeros everywhere, so this is in this, like the BP stabilizes this guy, because the sum around every plaquette is equal to 0 mod 2, it's just equal to 0 obviously. But if we applied an AV operator, so say we took this vertex here, AV is just the tensor product of these x's around all of these, it would change this to all of these guys to a 1. So if psi was the initial guy with all zeros everywhere, then AV is not equal to psi. So it's not invariant under the vertex operators. But if we took psi just to be every single a superposition of 0, 0, 0 plus 1, 1, 1 here plus vertex operators applied to every single vertex, then it would be, because if we had 0, 0, 0, you applied the vertex operator again, it goes to 1, 1, 1. That's still going to be in our superposition. So that's sort of just what I'm trying to get at over here. We have these individual state vectors that are stabilized by the BP, and then we take a superposition of them, and those superposition corresponds to all the same vectors in the same homology class of the dual graph. And the AV condition is saying that all the coefficients are going to be the same. So, if we had 0, 0, 0, so that's the one with zeros everywhere, and that was A alpha. And then we had plus B, A plus B. Should use different. Okay. So again, they're there on your sheet, but for this 3x3 case, which is the example in the notes, we have these superpositions. So yeah, in the notes I've labeled all the edges. It's going to take me a long time to do that again here, but basically this representative element of the homology class that corresponds to 1, 0, we're going to have, say, for example, 1s all along this guy, so co-cycle, or cycle in the dual graph, in the homology of the dual graph. That's going to be, say, this guy. And then you have the other homology class
through was ones on the parameter graph.
Yes, so
There was everyone else, which corresponds to ones along the blue edges that wrap around the torus horizontally.
yeah,
So he's drawing a cocycle.
yeah. And so you see this is still in the +1 eigenspace of all the BP, because, you know, if these are zeros everywhere else, that's still, you know, some to 0 mod 2, some to 0 mod 2, some to 0 mod 2. And then this. And then if we did the same thing this way, that's going to be the other cocycle, the other cycle in the dual graph. Okay, and that's what this one's going to be in here. So I'm going to use notation and call it this like that. And then finally, it's the one that's both. So if we had this one and this one. Okay. So they're four basis vectors for our code subspace. Do you want me to keep going and go through an example with error correction? Yes? Yep. Yep. All right, so we're going to consider this edge here. So it's in some state that's in the code subspace originally. And then we have an X error occur on this edge. So the four stabilizers that are involved with it are these guys, V, V prime, P, P prime. So just call psi this state before the X error. Sorry? Just some element of the code subspace. Yeah. So just an X error has occurred there.
Yes, this picture is X applied to psi.
Yeah. And so because the AV, so yeah, this guy is X applied to psi. Because the AV are tensor products of X, this commutes. So you have, right? So this error is still in the +1 eigenspace of AV and also for AV prime. But when we start applying the BP, they anti-commute. So and same for BP prime. So what's that's done if we measure these stabilizers, nothing seems to be wrong here and here, but something seems to be wrong here and here. Okay, so you'd measure it and you get the -1 eigenstate of each of these operators. And so basically the way that we correct for it is you're going to do an error correction operation that either applies an X here, or some series of X's that correspond to a homologically equivalent. So So if we observe this, we have the -1 eigenspace of these two operators. We don't know that an x has occurred here, because if we also had x errors on this one, and this one, you get -1, -1, -1, -1, that goes to +1, -1, -1, that also goes to +1, we have -1 here. So you can only detect the errors, you can only measure the -1 eigenstates at the end of like a chain of errors. So we wouldn't know if we just saw -1 here, -1 here. We don't know that an x has occurred there. It could have occurred here. It could have occurred some other longer cycle in the dual graph. But it doesn't matter, because we can correct along any one of those guys to fix that error. So we can either correct, if an x did actually occur here and we corrected x there, obviously that corrects the error because x squares to the identity. If we also did one along this chain in the dual graph, then x, x, x here, that's just a stabilizer. That this x has occurred there and we've also applied these x's, that's AV prime. And so that stabilizes the subspace. We still get back, it stabilizes the initial guy psi, so we still get back to the right vector. It's the same thing if we had, say, a z error occur on one of these qubits. The p prime and p double prime are fine. They're still, this state is still in the +1 eigenspace of the p prime and p double prime, but the AV primes are going to light up as a -1 eigenstate. So we can either correct for an error I'll put my blue pen. So if we can correct for a z error this way, or we could correct for a z error, say out here, or a big longer cycle. This time it's a cycle in the primal graph, then that's just a BP operator. So again, it just stabilizes the state. So long as we correct via a cycle, a chain of edges that creates a cycle that's equivalent to a product of stabilizers, we still get back to the same state. But the issue occurs if the issue occurs if we have more than one error, for example in this 3x3 case. So it creates a chain of errors and we then correct by a non-trivial cycle. So if a z error occurred here, z error occurred here as well. So we see a -1 occur at this, when we measure this vertex operator, -1, -1 cancels, so we don't see anything here, but we see a -1 at this guy as well. So we could have thought, oh, maybe a z error occurred here, so we're going to correct by that error. But if we do that, that actually acts upon the code subspace and gets you back to a different vector in the code subspace. So that's a logical operation. It's the same thing if we had, for example, x error, we see -1 here, and it wraps around -1 here, so we correct across this guy. Then we've acted on the code subspace, and we get back to a different vector, because as we saw earlier with these vectors, say, for example, we initially started in this guy, 2x errors occurred, and we applied an x error here, then we actually get to this guy. I hope that's a little bit clear for everyone.
So the bigger the lattice, the more errors.
Yeah. So in this case, this is just a distance 1 code for the 3x3 torus. Yeah. Yes, sorry, yeah, correct. Yeah. I think I'll probably stop there if there are any questions. I know some of that wasn't overly clear, but